Hello Vulkan developers and welcome to Texture Mapping Day. I assume that you are familiar with the general idea of texturing, and if you're not, then I highly recommend watching my OpenGL tutorial, which explains everything about texture coordinates and sampling from the fragment shader. The basic concepts of texturing are the same in Vulkan, it's just that the mechanics are different, especially on the application side. Now, the texture object in Vulkan is an image resource, and in many ways it is very similar to the buffer object which we are already using for the vertices. This means that to get texture mapping working, we will need to create and populate the image object with data and attach it to the pipeline using a descriptor set. Here's a high-level overview of the steps we need to take. Okay, before we get started, I'd like to say a big thank you to AB Irato, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev or by joining the YouTube channel as a member. Okay, so I'm gonna start with a new class called VulkanTexture, which is basically an aggregation of the 4 items that we need to do texture mapping. We need an image object, a device memory, an image view, and a sampler. We're going to go into more details in a minute, but this class should remind you of our buffer and memory class, which we're using for the vertex buffer. So here we have a buffer, and this is an image. In both of them we have a device memory. Because of the strange notion in Vulkan, where the memory of the object is actually separated from the object itself, and in addition to those two, we have the image view and the sampler. So I think that VulkanTexture is actually a better name than the buffer and memory, so maybe I'll change that in the future, but for now let's continue. So in the simple mesh structure, I've added a pointer to the VulkanTexture. And the reason that this is a pointer and not the actual object is simply for backward compatibility with the previous tutorials. So as you will see later on in this video, in various places, mainly I think in the graphics pipeline, we have checks for this pointer. So if it's a null, we simply know that there is no texture in this mesh. So it's not something that you need to have in your code. So now let's see the very few changes that we have in the Vulkan app class. As you can see, I've added a function called createMesh, which calls the existing createVertexBuffer. Right here, there is no change from the previous tutorial, and then loads the texture. Now in terms of the vertices, as you can see, I've added another triangle, because a single triangle for a texture is a bit weird. It's much nicer to have a square. So this guy goes from bottom left to top left and then top right. And then this one also starts at the bottom left and then goes to the top right and finishes at the bottom right. So if you're familiar with OpenGL, I'm sure you've seen that before. Now in terms of the texture coordinates, we've had them for a while, for quite a few tutorials. As you can see here, in the vertex structure, we have the texture coordinates, the 2D texture coordinates. So we just need to populate them correctly for the second triangle. Okay, so the bottom left vertex starts at the 0, 0 coordinate, same as this guy. And then we go to the top right, one by one, and then we finish at 1, 0. Okay, so no problem there. Now, to load the texture, we need to allocate a new VulkanTexture. Okay, remember that the new class is defined in the Vulkan core project, so it is under the OGLDev VK namespace. And now we can call the new function in the Vulkan core called createTexture. We provide a path to the texture, and we need to pass a reference to the actual VulkanTexture, so we dereference the pointer right here. And then the only thing that we need to do in this class is to send 6 vertices to the command draw function. So we may be getting these directly from the vector, but I just wanted to be very verbose in this case. So now let's see how to implement createTexture. Okay, so this function takes the file name and the reference to the VulkanTexture, and what it does is basically populate all the elements here. So first of all, we need to load the image pixels, and we're using the STB image library, same as in OpenGL. Then we create the image object and we populate it with the pixels that we have just loaded. Next, we create the image view, and finally the texture sampler. Going back to the first step, we load the image using the stbi load function, which takes the file name and an address of 3 variables for the image width, height, and the number of channels, which of course this function will populate. So we have them here. The final parameter tells stbImage that we want to load RGB and alpha. And the result is a pointer to this strange guy, which is an unsigned car. Now in my OpenGL tutorial, I talk more about the integration of the stb library into the application, but in general, since the library is entirely header-based, all you need to do is to include the stbimage.h file in your CPP code, and possibly also the stbimagewrite.h if you plan to write back into images. And there are a few macros that you need to define, this one is optional, before you include the headers. So I have a dedicated file for that, as you can see here, with those macros. And so in the place where I actually use the library, I just need to include the header without the macro. This is how I do it. If the result of stbi load is null, then there's probably an error with the file name or the file type is not supported. And in this implementation in general, whenever such an error occurs, it is catastrophic, so we exit. Next, we create the image object and we populate it with the pixels. So this function also takes the VulkanTexture, a pointer to the pixels, the width and height of the image, and the format. In this case, it's a Vulkan format, as you can see here, and we're using RGBA 8U norm. The texture format is always a source of some craziness in OpenGL as well as in Vulkan, but we're using this guy, which is pretty standard. So let's go into this function. As you can see, this function has 2 parts. First, we create the image, and then we update it with the pixels. To create the image, we have a new function, which takes the 4 parameters from this function, the text, the width, the height, and the format. And in addition, we also have a usage and the property flags. If you look up at how we create the buffer for the vertices, it is very similar. Usage tells us how we're going to use the image. In this case, we set the usage to transfer destination because we're going to copy the data into the buffer using a special Vulkan function, and also sampled because of course we're going to sample from it. The property flags is set to device local because we want the image to exist on the GPU memory, and this is what device local means. The function createImage is down here. And as you can see, we start by creating the image object by calling vkCreateImage. This function takes the device, the address of an image createInfo structure, and returns the result in the last parameter, which is of course the address of our image object in the texture, in the VulkanTexture class. Now this structure is very big, which is why I try to use as many default parameters as I could, which makes the interface of this function relatively simple. Okay, so for example, the image type is always 2D, the number of map levels and the number of array layers is always 1. We're not using multi-sampling here, so the samples is set to count 1 bit. The tiling is always optimal, no sharing, so exclusive, and etc. The parameters of this function includes the image width and height, which we set into the extent, but notice that the depth is always 1. The format goes here, the usage flags go here, but the property flags are not here because they will be used later on in this function. So we check for errors and hopefully everything went okay and we can continue. Next, we need to get the buffer memory requirements. And if you remember, we've seen this before with the vertex buffer. So if you search for this structure, you will see that we're calling getBufferMemoryRequirements for the vertex buffer, and here we have getImageMemoryRequirements. But the idea is the same. Provide a device, the image object, which was just created here, and an address of the memory requirements. And this will tell you, for example, the number of bytes that you need for this image. What we need to do is to allocate the memory for the image, and for that we need an allocation size and the memory type index. Now we get the allocation size from the memory requirements, so we're all set with that, but we also need the memory type index. And for that we have getMemoryTypeIndex, which we've implemented for the vertex buffer. As you can see, this is the function, we've seen this before, and this is how it's used for the vertex buffer. So as you can see, this is exactly the same thing. This function needs the memory type bits from the memory requirements and the property flags, which is why we provided that to the function as a parameter. So we call allocate memory on the device and the address of this structure, and we get the result into the VulkanTexture. And now all we need to do to finalize the image object is to bind the memory to the image object. So again, bind image memory does that, same as the vertex buffer. So we have completed the first part of this function right here, and now we need to update the texture image with the pixels. So this function takes the VulkanTexture, the width, the height, and the format, and finally the pixels. The process by which the pixels are going to end up in the image is very similar to how we populate the vertex buffer. And this means that we need to create a staging buffer, or a staging texture in this case, update the pixels into the staging texture, and then copy the staging texture to the image. And as you can see, we're going to use a lot of helper functions for that. So let's go over this one step at a time. We start by calculating the image size. And the image size is the number of layers times the size of each layer. And we're not really using layers at this point because this is a very simple 2D texture. So the layer count is set to 1, and the layer size is the width multiplied by the height multiplied by the number of bytes per pixel. And the number of bytes per pixel comes from the format. So we have a helper function which returns the number of bytes per pixel according to the texture format. As you can see, this is not an exhaustive list because there are many more formats. These are just a few basic formats that this function supports. So any unsupported format will take us here, and then we'll exit and we'll know that we need to add support for it. As you can see, there are a couple of formats here with 1 byte per pixel, and then there's one with 2 bytes per pixel, and a few with 4 bytes per pixel, or even more. In the case of our format, we expect to get 4. Now we can go ahead and create the staging buffer, which is really a buffer, okay? We're using a buffer in memory here, and not a texture. So we're using the same createBuffer function from the vertices. This function takes the image size, which we've just calculated, the usage, and the properties. So the usage of the staging buffer is a transfer source, because we're going to update it with a simple memcopy, but then use a command copy function from Vulkan to transfer the data to the transfer destination, which is the final buffer. And the memory properties are host visible and host coherent, and this allows us to do a memcopy to the buffer. Again, same as the vertices. So no need to go into this function. We already saw that with excruciating details in that video. What we can now do is call update on the staging buffer with the device, the pointer to the pixels, and the image size. And what this function does is to map the memory. We get the address of the buffer contents right here as a simple pointer. We do a memcopy from the source to the destination. This is why we need the size in bytes. And finally, we unmap the memory. Next, we need to copy the staging buffer to the image object. But we cannot just do a copy command like that. We have to do a couple of layout transitions. And we talked about the layout in the video on image memory barriers. So in this case, before the copy takes place, we need to transition the image from layout undefined to transfer destination optimal. And after the copy, we transition from transfer destination optimal to shader read-only optimal, because we're going to access the image in the fragment shader, where it is of course a read-only object. The function that does the transition is called transition image layout. It takes the image handle, the texture format, the old and the new layouts. And it is implemented down here. Now the main thing in this function, as I said, is the usage of the image memory barrier to perform the actual transition. The Vulkan function that implements the barrier actually operates on a command buffer, and here we have basically two options. We can either create and then destroy a dedicated command buffer for this, or we can reuse an existing command buffer. Now, since this channel advocates a responsible approach to conserving energy and the environment in general, we're going to reuse a command buffer which we've already created and is currently unused. And what I mean by that is this guy, this copy command buffer, which is a private attribute in the Vulkan core class, as you can see. And this is a command buffer, which was created in a previous video specifically for the task of copying from the staging buffer of the vertices to the final buffer. When recording stuff into a command buffer, you have to be careful about synchronization and make sure that only a single thread at a time records into the command buffer. We can use external synchronization mechanisms for that, but even better is to allocate a dedicated command buffer to each thread, and then they can record stuff in parallel into their respective command buffers. In our case, since this code is single-threaded, we can simply reuse the same command buffer. To initialize the process of recording, we have to begin the command buffer, so we use a wrapper function called begin command buffer, which we've seen before, which takes the handle of the command buffer and some flag. In this case, we use the one-time submit bit because we don't plan on submitting this command buffer more than once. This function is implemented in wrapper.cpp, and it is a simple wrapper around the Vulkan API vk-begin command buffer. Simply saves us the hassle of setting up this structure. After handling the barrier, we call submit copy command, which is a helper function that does three things. First, it ends the command buffer, then it submits it into the queue, and finally it waits for the queue to become idle, which means that the command buffer was executed and can now be reused. As you can see, this function doesn't take any parameters because it always works on the private command buffer. You can see that we're using this function in several places in the code. In addition to the transition layout, we also use it in the function copy buffer to buffer, as well as copy buffer to image, which we're going to see later on. Okay, so it's very useful. So let's go back to the transition function and take a look at image mem barrier, which is also a wrapper function, which takes the command buffer handle, the image handle, format, old and new layouts. This function is a new one, and it is implemented in wrapper.cpp, which is where I keep various wrapper functions around Vulkan APIs. The way that the image memory barrier function works is that it takes this big structure right here as a parameter. Now, several of the attributes are hard-coded for simplicity. For example, the aspect mask always refers to a color image rather than depth or whatever. Base mipmap is always 0, base layer is also 0. The number of mipmaps and layers is always 1, and etc. We may extend this in the future, but for now these are okay. We also use the function parameters, the image handle, and the old and new layouts. If you remember the tutorial on the image memory barriers, there is this notion of a source and destination access masks and stages that we need to set for the use case at hand. We already talked about these parameters in the previous video, so very briefly, the source stage mask specifies the last pipeline stage which wrote to the image, and the destination stage mask specifies the next stage which is going to read from the image. The source access mask specifies how the image was written. For example, was it written by a shader or by a copy command, or did the CPU map the image and wrote to it? There are many possible options. The destination access mask specifies how the image is going to be read. And again, this may be a shader read, or the source this time of a copy command, and etc. Now choosing the correct access and stage masks can be quite complex, so what I did is simply to copy the code from the 3D graphics rendering cookbook, which takes care of everything. As you can see, there are many cases here that check both the format and the layouts. Specifically in this video, the transition from layout undefined to transfer destination optimal, which is done before the copy, sets the source access mask to 0, because this is layout undefined, so we don't really care, and the destination access mask is transfer right, because we're going to copy from the image. And then the source stage is the top of the pipeline, because basically there's no activity on the image at this point, and the destination stage is where we're going to write to the image, which is a special stage called transfer. And then to transition from transfer destination optimal to shader read-only optimal, we have this piece of code right here, where the source access mask is the previous destination access mask, which is transfer right, and then the destination is a shader read, because the fragment shader is going to read from it. And then the source stage is stage transfer, which is the previous destination, and then the current destination is the fragment shader. So if you want to simplify the code, you can simply include these two cases and place an assertion if the case is different. Hopefully this function will make our life simpler down the road. So once we're through with all those checks, we get to the actual barrier function, which takes the command buffer, the source stage, the destination stage, and the address of the barrier. You also need to specify the number of barriers, because this can actually be an array, and then you place the number of elements in the array here. We don't use these guys in this case, so don't care. Now that the transition to transfer destination optimal has been completed, we can go ahead and copy the buffer to the image, the staging buffer to the image. So this function takes the image handle, the handle of the staging buffer, the width and height of the image. The function that does the actual copying is called command copy buffer to image, and it also needs a command buffer, so we're going to reuse the same command buffer from before. So we have the same function called to the begin command buffer wrapper, and finally we submit the copy command. This function takes the handle of the command buffer, the source buffer and the destination image, the layout of the destination image, and a bunch of parameters in this structure. So again, most of the stuff here is hard-coded for some defaults, and the only thing that we need to set is the image width and height. As you can see, the source offset is always 0, the destination offset is always 0, and the depth is 1. You can see that this function is very similar to copy buffer to buffer. It's simply that this one uses a simpler function called command copy buffer, whereas this one is command copy buffer to image. But the idea is very similar. This one, of course, was used for the vertices. Once the copy operation has been completed, we transition the layout again, now from transfer destination optimal to shader read only. At this point, the image is ready to be used, and we can get rid of the staging buffer or texture right here. Now I want to point out a very important thing, and that is to make all this stuff work in terms of using and reusing the command buffer, we have to make a minor modification to the way that we create the command buffer pool. What I did in this function is to change the flags in the command pool create info from the original 0 to reset command buffer. And this allows us to call begin command buffer over and over on the same command buffer handle, which will implicitly reset the command buffer to the initial stage. If you leave this 0, then you will get various errors or warnings or whatever. So we have finished with this function, and at this point our texture object is fully populated with the contents of the image file. So what we should do is release the memory that was allocated by stb image, because there is no point in keeping it around. Okay, so we call stbi image free on the pointer to the pixels. And now we have 2 steps left in order to complete the initialization of the texture so we can bind it to the pipeline. And that is to create the image view and the texture sampler. So the notion of the image view is not new to us. We've seen it when we created the swap chain and the images in the swap chain. Because in Vulkan, you can't work directly with an image. You have to create an image view, which is yet another source of indirection, kind of like a window into the image. The image view allows us to restrict the access to the image, for example, just to a certain MIP level or an array layer, or change the format at runtime, stuff like that. So what we will do is to reuse the function createImageView, which was also used for the swap chain. And I've made a couple of changes to this function. First, I reduced the number of parameters to make the API simpler. So now it takes only the device, the handle of the image, the format, and the aspect flags. The aspect flags tells you whether this is a color image or depth, stencil, or whatever. And the second change is that this function was moved from this file to wrapper.cpp, which makes more sense. But other than that, it's the same function. Okay, so right now the creation of the image view is hard-coded to a 2D image. And we have these settings for the base MIP map, level count, array layer, and layer count. So we only need to provide the image handle right here, and the format, and the aspect flags. We get back the image view handle right here, and we return it back to the caller. So if everything is okay, we save the image view handle in the VulkanTexture class member. Next, we create a texture sampler. Now, the texture sampler is kind of like the mechanism through which the sampling will take place. So all the parameters that you remember from OpenGL that go into the GLTextParameter function are handled by the texture sampler. And this includes the filtering type and the addressing modes and a bunch of other stuff. So I created a wrapper function for that called createTextureSampler that takes the device, the minimum and maximum filters, and the addressing mode. And this function is also implemented in wrapper.cpp. As you can see, we have a lot of options to configure the texture sampler. And right now, most of the configuration is hard-coded. So for example, the MIP mode is linear. There is no LOD bias for the MIP maps, and a few others. So we provide the minimum and the maximum filters, and they go here into the structure. And the addressing mode is the same for the 3 axes. We can now call the actual Vulkan API VKCreateSampler with the device, the address of this structure, null for the allocator, and we get the result here. And this is a handle of the sampler, which is returned back to the caller and is also saved into the VulkanTexture class. So now the VulkanTexture is ready and we can bind it to the pipeline. There are not a lot of changes to the graphics pipeline class, so we can easily go over them by comparing to the previous version. As you can see, there is no change to the interface of the constructor. We get a pointer to the simple mesh, which now contains a pointer to our VulkanTexture. The constructor calls createDescriptorSets and passes in the pointer to the mesh. And then this function calls createDescriptorSetLayout with the new parameter of the pointer to the VulkanTexture. As you can see, this function works by setting up a vector of a VKDescriptorSetLayout binding structures. We already have one structure for the SSBO and another one for the uniform buffer. So we create a third instance for the fragment shader layout, and we set the descriptor type to combined image sampler. Okay, this was a uniform buffer, this was a storage buffer, this one is combined image sampler. We have to allocate the binding point, so we set it to 2 because 0 and 1 are already taken. The descriptor count is 1, same as these guys, and the stage where this binding will be active is the fragment shader. These two are set to the vertex shader, but we're not doing sampling in the vertex shader, only in the fragment shader. And again, for reasons of backward compatibility, we check whether a texture really exists in this mesh, and if it does, we push the new structure into this vector right here. And now the layout can be created as usual, and we don't need to make any more changes because the structure that this function takes sets the number of the binding points directly from the vector. So this will be 2 or 3 if we have a texture. After the descriptor set layout is created, we allocate the descriptor sets and then update them with the handles of all the resources. And this is going to be the final change in the graphics pipeline class. We prepare a structure of the VK descriptor image info type. And this guy has 3 elements: a sampler, an image view, and an image layout. The image layout is actually an enum with various options such as color attachment optimal, depth stencil, shader read-only, transfer, and etc. Lots of layouts here. So we set the sampler using the sampler handle in the VulkanTexture, in the mesh. Same thing for the image view. And we set the image layout to be shader read-only optimal. And this makes sense, right? And now we need to use this in a new element in the VK write descriptor set vector. So we already have 2 elements in this vector, one for the SSBO and the other for the uniforms. So we check if we have a texture in the mesh, and we push a 3rd element for the sampler. So we need to set the correct binding point. The destination array element and descriptor count is the same as these guys. Descriptor type is again combined image sampler. And finally, the VK write descriptor set contains a few pointers to the actual data, because we don't see any handles here. As you can see in the case of the SSBO, we set the p buffer info pointer to the structure that contains the vertex buffer handle, and the same for the uniform, only that this guy contains the handle of the uniform buffer. But since this guy describes an image, we use the p image info pointer and not p buffer info. Okay, so this pointer now points to this guy right here with the information on the sampler and the image view and the image layout. The call to VK update descriptor sets also uses the size of the corresponding vector, so everything works out of the box. So now everything is set up correctly on the application side, hopefully. So all we have to do is to update the shaders to sample from the image. Okay, let's start with the vertex shader. As you can see, I've added an output variable for the texture coordinates. This is almost the same as GLSL in OpenGL, except that we have this layout specifier here, which tells us that this variable is mapped to location index 0. So in OpenGL, the compiler usually takes care of that, but in Vulkan, we have to do it ourselves. So for example, if we remove this, try to run the code, then you can see that we're getting an error that Spear V requires location for user input and output. So from now on, make sure to add these location indices to your code. As we saw on the application side, we already have the UV coordinates in our vertex structure. So all we have to do is to write to the texture coordinates output variable from the vertex that we have pulled from the buffer. Okay, remember how we do vertex pooling? Define a vertex data variable, extract it from the vertex array or vertex buffer here, using GLVertex index as the index, get the position, and the same thing with the textual coordinates, except that this one is a vec2 and this is a vec3. And that's it for the vertex shader. On the fragment shader side, we have to define a corresponding input variable, and also make sure, of course, that this is the same location, otherwise there'll be a mismatch and an error. And here we also need to define a uniform variable for the sampler. So this is a sampler 2D, and notice that in the layout specifier, we use binding and not location. Okay, so this is for variables, this is for resources, and this, of course, needs to match the configuration in the graphics pipeline. Okay, we have the vertices on binding point 0, the uniform buffer of the vertex shader in binding point 1, and this guy goes on 2. Okay, so this is like a global index for the entire program. And now we can sample from the texture using the UV coordinates. And this is now the output color. So this was a very long tutorial, but unfortunately with Vulkan, we have quite a lot of details that we need to take care of to get texture mapping up and running. If you've seen the entire video, then thank you very much for watching, and I will see you next time.